And then I will share I'm going to try just sharing this whole desktop this time so I can easily change things around. There we go. What are you going to that there? Okay. Can you see my desktop now? Oops, I get back. Yes, you can.
Yes.
Okay. So if anything's hard to read, just let me know, stop me, because it's hard for me to judge how it's going to look on your screen. So this is some charts. These are some slides I put together for the book club. And this is kind of an interesting thing. I didn't really have time to do that. So I said, hey, let me just try Claude Code and say, hey, take a look at this previous week's slides, chapter slides. Take a look at chapter 2 of the book, gave it the link to the book, right? This. And put together some charts, some slides in Corto, exactly the same format. I did a pretty good job. I made like one small tweak to it. So everything you're going to see in terms of slides was made by Cloud Code, made by AI, by agentic AI. It's pretty amazing what you can do these days.
Yeah, I know
And
there's so much now that they're able to do.
and I recommend anyone if you when you take anyone listening, if you take on a chapter um, of this book, feel free to try that out. I mean, you can save a lot of time. After you've gone through the chapter yourself, you could let Claude Code or Codex or any of these agents make some Corto um, slides for you, then go and change them to how you really want them to be. But you might find they're a good start. Like if this was by the time I would have gone through and maybe made some more changes, but it's actually not too bad, as you will see. So this chapter is about the mathematical building blocks of neural networks. And the main objectives here, as it says, is to understand what tensors are, because that's the main thing we play with deep learning, and learn the basic operations. There's really only like three, maybe four operations, depending on how you count them, that determine all of the operations that happen in any deep learning thing, including Claude Code or any other uh, generative AI or just simple neural networks. They're all based on these relatively elementary operations. So we're going to talk about those are, and then we're going to just go through how gradient descent works, which is the main engine of training uh, these deep neural networks, right? So as an example, and we'll also look at the code for this too, he uses the MNIST data set. This is kind of the hello world of machine learning that everybody starts with. Although nowadays they're starting to also use this thing called the fashion MNIST, I think, which uses pictures of clothing instead of just digits. But this was the kind of the first problem that people generally solve with deep learning because it's easy. The idea is you have these digits that are handwritten digits. And then also you have 60,000 of these images that are labeled, and then 10,000 that are also labeled, but you hold off on, you don't train on those, use those for testing. They're small, 28 by 28, which is easy enough to run on your computer or on Colab. So it really is a good exercise to go through this process. And I think it'll come back again in the book, but in this chapter, we're going to do it relatively quickly. So in this chapter, he presents and just the complete, end of the story. If you have Keras installed, you can train a network to do that job in as little as this much code right here. Um, but you're not expected to understand that yet. This will be something that'll be revealed in later chapters exactly what's going on here and exactly how you use Keras. But the idea is relatively straightforward. You're just saying, hey, my model is a sequence of two dense neural networks, and that's it. They're just connected together automatically for you with a sequential operator. And then you compile it, you tell it what kind of optimizer you want to use, you tell it the loss you're going to use. All this will become clear later, and any metrics you want to track, and then that's it. Tell it to train it. So we will uh, go through some more detail of what's happening here as we go, though. So taking a big step back, what exactly is a tensor? So a tensor is nothing but a set, in some sense, a mathematical structure organizing numbers. So and they increase in rank. The lowest rank, the rank zero tensor is just a number, just a scalar number. Then the next up is just like a list of numbers called a vector. I guess you should call it a vector, not a list, because a list can be a list of anything. Like they don't have to be all the same thing. Whereas a vector, the list, every element is the same type, and that makes a vector. That's a tensor rank one. Tensor rank two, you add another dimension. Now you got a matrix, and then you can keep going up and up and up and up. And the terminology is the number of dimensions, ndim, is the rank. The length of each one is given by the shape. So the shape gives you like here's a rank 3 tensor, and you can look at the shape, which will tell you the size, how many elements across each dimension you have. And then finally, what also matters what the data type is for the elements in the tensor. So this just matters some terminology to learn. So you will use vector data, which is generally going to be um, like tabular encoding, just bigger tabular data, encodings of embeddings, I'm sorry, of other things like categorical variables. You can make embeddings. That'll become clearer later. By the way, this is kind of weird because I said, hey, this is a vector, but this has actually got NDEM too, and that's because we also have this sample dimension tacked on. So the actual data is a vector, but then when we batch it together by samples, we end up with actually a matrix here, as you can see. Then we have time series data, where now we have a time step as well as the features along those time steps. Images, which we'll be working with a lot, height, width, and channels. And then finally video, which now adds another dimension of the time or frames in this case, like movie clips. It's just meant to be some examples. And here's another way of looking at it. Like in your picture, if you want to have a picture in your head, this is a time series as a 3D tensor. Each sample is a 2D tensor, features by time steps, but then when you add the sample batch dimension, the sample dimension, you end up with a 3D tensor. I keep going back between samples and batch because that is the name of this dimension. It's used interchangeably. Same thing if you have images, right? Now you have these big blocks that are there. Each image is actually a 4D tensor because we not only have the height and the width, we also have different colors for a color image, and then the samples themselves. So it's hard to visualize, but this is one way to kind of try to visualize the 4D tensor. And we won't try to go any further than that. That's as far as we're going to go. Excuse me. So let's talk about these tensor operations. I think it's easier to look at it in the code. So let me just move this aside for a minute. We don't need this either. Okay. So now you should be able to see my Visual Studio Code window. Um, and this is a notebook that you can get on the GitHub for the book. I didn't write any of this. This is all from the author of the book. The cool thing here is using Visual Studio Code, you can go into your extensions and enable a collab extension, install it. And it allows you to do is to, oops, I don't want to see that anymore. When you select a kernel, if you for your notebook, you can say, hey, give me collab. And you have to have an account, but I already connected to my account. The first time you do so, it'll ask you to log in. And I'm going to say, give me a Python kernel. Now I'm connected to Colab and I can just execute things. It won't be on my machine. This fails like this every time. I don't think you even have to execute this. I think these things are already installed on the Colab thing, but it does something that it complains. And so this notebook you can download from the book's website and do this kind of thing yourself. These are just some things to get things set up. But inside Keras, is this font too small? Can you see this? Should I make this bigger? Can I make it bigger?
I can't see it, but I think it will help to make it bigger.
I've actually forgotten how to do that. I think it's in here. Editor. Increase
I
edit.
know on Windows it's Control plus, so maybe on Mac it should be Command plus.
I think that'll make everything bigger. I just want the font bigger.
Ah, I see. Yes. That will
And
make everything
there's a
bigger.
command for it. This one right here. I don't know if I have to do this over and over again. There's probably some better way to do this. That's probably better, right?
Yeah, no, significantly better.
Okay, so you can load in from Keras has built in this data set, this MNIST data set is so commonly used for teaching machine learning that's built into Keras and built into many other of the machine learning, not just deep learning, but machine learning libraries. So we can just execute this and it'll just load in the MNIST data. And as we said before, um, well, it takes a minute, so it actually hasn't downloaded again. Great. Okay. Oh yeah, of course, this is a brand new instance on the thing. And you can see, yeah, there's 60,000 training images, and each one of them is 28 by 28. So it's sample dimension, width and height. That's the same thing again. And we can just take a look, like, for example, at the labels. So let's look what we got. We got images, we got the labels for those images, which tells us what they are. We got test images and also test labels, which are the same structure, just less of them. And those are what we use to verify or to check our accuracy. Because we have in machine learning, as you're probably well aware, what you do is you like to hold out a test set to check at the end uh, and get an unbiased measurement of your accuracy of your model. Okay, so here, this is just exactly that code that I showed in that slide, right? So we're just going to import Keras and just define a neural network. Very straightforward. It's a relatively high level interface, which is what Keras represents. In the back end can be anything. I think I set the back up here somewhere, didn't I? Yeah. So we set the back end to be TensorFlow, but you could set it to be JAX and or PyTorch, and that'll be something that'll be discussed in the next chapter. So we can define this model. That's pretty straightforward, right? It's just a couple lines, and we now defined a two-layer, kind of the minimum neural network you can have, fully connected uh, perceptron, I guess they call it. Compile that model with the atom optimizer and the uh, categorical cross-entry loss. Now, there's one little trick here. We have to take the images and flatten them out because this network takes just takes the flattened representation of the um, images. So we're going to flatten them out. This is this reshape operation. Actually, maybe it makes sense to go back. Well, so I'm not going to go back. So this is one of the things you can do to tensors that's important is reshape them, like change them from two-dimensional to three-dimensional, or three rank to two rank. Here we're changing it from a rank 3 to a rank 2. And the other thing we're doing is just making sure that the images all are scaled to 0 to 1 because that's what these models expect. They're originally were integers to 0 to 255, but now they've been changed into floats from 0 to 1. That's all that. This is just a little bit of data pre-processing that you need to do. And now we want to fit the model. So that's just a one-line thing too. And we won't worry about the details yet, but at some point we will discuss what these different details are. But the idea is that we are using we're doing this batch-wise. So there's 128 is the batch size. And that means it's showing the network 128 of these at a time. And we're going to go through the entire set of training things 5 whole times. That's what this epoch is. And this is not too bad, right? It's not too slow. And you can see as it goes, the accuracy is increasing with this accuracy on the training data, mind you. And then the loss is going down, which is what you'd expect to have happen. That's only on the training data. The accuracy is very good on the training data, but we should check what it is on the test data. And that's what we're going to do here. Well, first, we're just going to take one of like the first 10 images and see what it predicts. Actually, we're going to look at only the first image. And when you run the model on like the first 10 images, or in this case, we pick out the result from looking at the very first image. What it comes back with is a 10-dimensional array, which is the probability that it predicts that that image is that particular digit. And if you look through here, you can try to see which one's the biggest, or it's actually this one pretty by a lot, right? This is 0.999. I don't know which digit that is. It's the 7th digit. So it's saying, hey, this is probably a 7, right? Well, let's see. Was it a 7? Yes, it was a 7. And we can check them all much faster by just using this function called evaluate, give it the test image and the test labels, and it'll come back and just tell us that on the test data set, it did do pretty well. Actually, 97.5% or 97.6% accuracy in the test data set. So that's kind of just quickly going through a whole end-to-end run on what this looks like. This is something we will learn to understand better, presumably through the rest of the book, is what I'm getting out of that. Let me see, should I go back to the charts here? No, let's just keep going here. This is more interesting. Just tell me if you want me to do something different. I think that going through this notebook is kind of
I,
useful.
I also prefer this is much more better.
Okay, cool. So the this is just showing you again how you represent. Now we're going to go to use NumPy, but it's the same in NumPy as it is for JAX as it is for PyTorch in essence. So we're going to use NumPy to just illustrate some of these points of how these tensors are represented. So first in NumPy, we can represent an array as, I'm sorry, tensor as a numpy array of a scalar numpy array, and we get an output. It's just the number 12, but now it's wrapped in this numpy data type, which helps numpy know that this is something I can do faster work with. Because numpy is designed to very quickly process these numpy arrays and tensors. Not as quickly as PyTorch because it's not using the GPU, but on the CPU, it's still faster than trying to do it with like Python, which is interpreted language. And we can define a rank 1 tensor, just an array, simple array of numbers. We can define matrices, which are rank 2. We can ask for the shape of them, just like we did with the Keras tensors. It's all the same. Higher rank tensor, still the same. It's all very straightforward in terms of how you represent these things in Python. So let's go back and grab these images again and just understand the key attributes of these things, which we mentioned before. But again, the images, what's the rank? It's 2. It's 3. Sorry, it's 3. Yeah. The reason why that had 2 there because I skipped this step last time we did after we flattened them. So it's 3. It's sample dimension, and the 2 hits the width and the height. So that makes sense. And the shape now will be 60,000 of them. On the first dimension, 28 by 28 is the actual shape of each individual image. The D type, that's another thing. They're integers, like I said before. And then we can also take a look at them. We can load in PyPlot and just look at our matplotlib and just take one of these images and use the image show to see that that's a 9. And that's the kind of thing we're going to train on. Better be a 9 on the image label. Yep, it is. Good, good. Everything's good. All right, so that was just tensor attributes that we talked about before. Now we're going to look at what I was saying before about manipulating tensors. This bit of business here is just about like, hey, you could take this is some NumPy, but this same kind of notation works for, and this is something you really should experiment and play with to really understand. It really pays to spend some time with these and just use NumPy. You don't need to use anything else, which is easy because NumPy is already probably installed in your data science stack, so it's already ready to go. You can, or on Colab, you can do this. It's also already installed on Colab. So what we're doing here, we have train images, which as you remember is 60,000 of them. This right here takes a slice of them. Takes a slice of the from the 10th through the 100th. Every other dimension is not mentioned, not explicitly mentioned, is just carried forward through. So you can see here I've got 90 by 28 by 28. That's one way to take a slice. This does the same thing. If you want to explicitly put colons in here to indicate that you are going to take all the elements from the other dimensions, you can do that. This does the same thing. You can explicitly say, I want these particular width and height of the thing, or I could take partial slice. So here, I'm going to take all the images, but I only want the lower right corner, I think that is. I think it's lower right corner of each one. Or the middle, which is what I think this indicates. Um, so let's see. So taking this first operation where we just took the images and took a slice across the sample dimension is actually extremely important in machine learning because that's kind of how we make batches. So if we do this, we get a batch of 128 of the 60,000 images that are in the training set. We're going to take the first 128 and 120 of them and call that a batch. The next batch will be from 128 to 256. And then we can take the third batch. We can just follow this pattern and keep getting batches that way. Okay, so I think we're caught up to the slides now. This is just where I talked about that. Now we're talking about tensor operations. So the tensor operations kind of happen, like I said, in a 3 or 4, depending on how you want to count them. I forgot how we did it in the book. But the first one is element-wise. That's the most straightforward. You're just going to take every element of the tensor. I don't care what shape it is, how many dimensions it is, every single one individually, multiply them by 2, divide them by 3, or whatever. Do something to them. The most common element-wise thing you might do is this ReLU activation, which is nothing more than if the number is less than 0, make it 0. Otherwise, leave it alone. That's the rectified linear unit, as they call it, but it's nothing fancy. All it is just taking the max into 0. And this is how you could do this naively. You would never do this because this is slow in Python loops, but this is how you would do it slowly. Your libraries have fast versions of this. But you can see all I'm doing here is taking the whatever. Actually, this is also bad because it assumes a matrix only, whereas the built-in ReLU will work for any tensor. This will only work for a shape 2 tensor matrix. And all it's going to do is walk through the matrix, and for each element, element wise, right? We're going to compare it to 0. If it's less than 0, well, this is what the max operation does, right? It's the maximum between that element and 0, which does what I said. So if it's negative, it's going to be 0. If it's positive, it's just going to return what it was. We could also do this naive add where I take two vectors that have to now be the same shape, right? Because you're going to do element-wise add, they should be the same shape, with an exception I'll explain in a minute. Now we're just going to elementally wise add the two uh, matrices together. That's element wise. I don't know if I need to define these, so I need them later, but I will. So this is, of course, very slow. Here I'm going to add two. Well, okay, it's not that slow. But oh, no, so this is fast. This is fast because here I'm just doing it directly. I'm saying take this big, not big, but this relatively, I don't know, this matrix, 20 by 100 is not big. This matrix, these two matrices, add them together, do the ReLU using maximum from NumPy. This is fast because this is using NumPy's compile code to do it. If I use my naive one, that should be slow. Oh, did I not define one of these things? I guess I forgot to define the ReLU. If I use the naive one where I do it in Python loops, it'll take a couple seconds, right? So you don't want to be doing your own loops. You want to let the loops be in C, which is what's going to be happening in there with NumPy. And with uh, PyTorch, it's actually going to be on the GPU if you have GPUs to use and you have it configured correctly, which is always fun. Okay, so that's one concept. The next concept is broadcasting. So the idea here is relatively simple. If I have two tensors that are not the same rank, I still might be able to add them together if the NumPy or PyTorch or whatever you're using can figure out how to broadcast across the other dimension. Basically, the axes are compared one to one, and they're either equal, or if they're missing, then it can treat it as if it was a one. You can do this manually, though. You can say, okay, take y and expand it along one dimension to make it um, now instead of being, oh, did I not define the right way? Oh, hold on, try that again. There we go. Now y is, instead of just being a 10-dimensional vector, now is a 1 by 10. It's exactly the same, but now it's got, maybe you can think of it as the same, but now it's got extra parentheses around it, or extra brackets around it, if you want. You can also use this tile thing, which I forgot exactly what this does. I'm tiling it after the fact. What does y look like? Okay, that's a mess. Right, so what this does is just repeats it across the other dimension. So now I have a 32 by 10 uh, matrix, except now each of the 32 copies is exactly the same as this 1 by 10 original vector. Again, I don't think I'm doing a very good job explaining that, but the point of all that was so you can then take two things that aren't quite the right, like I can now define a new function, add a matrix and a vector, and what it will do is it'll expand. Actually, it doesn't even bother here because let me back up a second. Like I said, I'm not explaining this very well, but what you should do is go through, do these yourself and follow along in the book and make sure that you can kind of understand how this broadcasting thing works. It still trips me up all the time, by the way. And my usual approach is I'll just try and see if it'll work. If it does what I think it's supposed to do, I'm happy. If not, I'm like, okay, I must have got something. Maybe I need to extend an axis somewhere by hand or something. And I think everybody kind of does that in my experience. But just to show the mechanics of it, rather than in 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 NumPy or in any of these languages, rather than explicitly expanding things and tiling them like this before it adds them together. Oh, that was the point, you're right. So the point of this was that I want to add these two together. To do that, what NumPy in principle does is it expands this x y thing to match the shape of the x. The y vector, it turns it into a matrix that matches the shape of x. And it, in principle, it does that by making 32 copies of it so it has the same shape, and then we can add it together. And that's what this whole demonstration is for. But in reality, it does something more like what this Python code illustrates. It simply it doesn't need to actually make those copies. It just simply adds the same y over and over again for each I, right, in the loop. But this, of course, would be slow um, if we actually ran this. But this is what's happening essentially. But it does it in C or in the GPU. Okay, so that's that part of it. Um, and this just shows it in action, right? So here I have two random uh, tensors. One's rank 4, one's rank 2, but I can still take the maximum between them because it'll just broadcast between them two. And then Z will have rank 4 now, presumably, if I understand anything at all, which is potentially doubtful. Yeah. So now you can see that Z has the same shape as X, and that's how they made it compatible by basically making X, Y in principle a 64 by 3 by 32 by 10. It's expanding the other axes that are missing. And that's basically that. Okay. So that's the broadcasting operation that happens. And we're almost done trucking through these operations. And I think it's worth for anybody going through this chapter to go through this again, just to make sure you understand it. Now, the big operation, the core operation in the neural networks where things are actually happening, where things are getting mixed up and representations are being built layer by layer, is this matrix multiplication or tensor product, as it's called more generally. And if you know linear algebra, well, you already know what a matrix multiplication is. But essentially, it is a way of combining two matrices to make a third matrix um, by multiplying the rows of one by the columns of the other one. And to do that, the size of the rows of one have to be the same as the columns of the length of the other one. So this just does this explicitly in naive code again. For this is a vector. So the reason why I call it tensor product is you can multiply different size things. So here I'm actually just multiplying two tensors together. This is called a dot product because what you're doing there is just simply multiplying. Well, it just shows right here, multiplying element by element from the first element of X times the first element of Y. That's the first element of Z. The second element of X times the second element of Y. That's the second one of Z. That's a dot product. It's something you learn. And when you get done with that, what you actually end up with is a scalar, just a number. I think we can just run that and verify. Why did I write code? I don't know. Yeah, 7.5, whatever. It's a number. But we can also do matrices times vectors in a similar way. So now we're taking but now we end up with another vector because we're taking each row of the matrix and doing essentially this dot product, right? So remember that we just talked about a vector dot product. We take two vectors and we multiply them element by element and then add them all together, kind of what you do. Um, the When you multiply a matrix by a vector, you get a new vector out by the first element of the new vector is the dot product of the first row of the matrix times that vector. The second one is the second row times that vector, and so on. This is all explained better in the book. It's essentially elementary linear algebra. But he does explain exactly what the math is. No trickery. This is the math. Um, and finally, what's the difference between these two? I do not know. Matrix vector. Oh, right. So he's just explaining what I just said. You don't actually need to do this. You can just use the vector product because really it's just by row, do one row, vector product, the other row. And finally, the matrix product is now expanding out the other dimension where each element of the new matrix is what that dot product was of that row I and column J of the row I of the first matrix, column J of the second matrix, dot product together. What that number is, that goes to that matrix at that IJ spot. And I'm sure that I'm doing a terrible job explaining this, but it's all in the book. And the math is here. If you know linear algebra, it's very straightforward. If you don't know linear algebra, it's worth learning it, I think. Okay. We already talked about tensor reshaping. This is what we did when we took those train images and we flattened them out before. So I'm not going to bother going too far into that. But that's the basic idea. So the essential idea is those are the main operations. Everything boils down to that. And it's kind of fun to think about, like inside GPT 5.2, essentially that's what's happening. Linear algebra and element-wise operations, particularly like ReLU and softmax and things like that. Let me just move this slide back over here so I can just, I think the next part is just about this geometric interpretation. So the book talks about the idea that, hey, this dense layer is essentially can be thought of as geometrically as doing the matrix multiplication is kind of like a rotation of the representation, and then the ReLU is a nonlinear operation, like in this case, just chops off anything below zero, as you can see there. So that's one way to look at it. It's like we do a transformation, rotation, translation. That's the dense less layer. Rotation, matrix multiplication, and then there's usually you got a bias. That's the B here. Oh, here it is, right here, right? So the weight matrix multiplied by the input vector, and then adding a weight bias vector. Weights and biases. You probably heard that before. There's a podcast by that name. And that offset is the translation. So it's a rotation in a high dimensional space plus a translation. That's a linear operation. That's all it is, called an affine transformation. It's a linear operation, but then we make it nonlinear by applying this ReLU. And it's important to do that nonlinear operation because if you just stacked dense linear operations like this, you can just algebraically combine them into one single linear operation. Nothing interesting happens. So you have to do something nonlinear. And it turns out it doesn't really matter that much what you do. For a long time, people use like tangent, hyperbolic tangent functions and other things, but the ReLU is very simple and fast, and people have kind of settled on that for most of the output of these dense layers. It's called the activation function. You probably heard that before. Okay, so and then the book mentions this paper ball analogy. You can imagine that the idea is that your initial data is some kind of crumpled up ball. What we want to do is to use the deep network to uncrumple the ball into some nice representation, flat piece of paper so you can understand it and then make predictions based on that. So this is showing what the training loop looks like. And I think maybe it might be better to go back to the code for this, but just going through it quickly. The idea of the training loop is we have all these training samples. We draw a batch at random, a small batch at random from the training. Well, actually, that's not quite true. We batch up it randomly because we do need to go through all the training samples. We batch up all the training samples randomly. Then we take a batch of those, a smaller subset of them. We run that through the network to make a prediction. The prediction is going to be wrong. Well, how wrong, in what direction, what matters? So we compute the loss, how wrong it is, and then we calculate the gradients. We'll talk about that in a second. Basically, gradients meaning what direction was it wrong in, right? And then we're going to push all the weights to move them opposite the gradient. And then just keep doing that until you get to low enough loss or until you ran out of time or whatever. um, that's the training. That's basically the training loop that everything is trained on for supervised learning. So we do need to talk a little bit about the gradient. This isn't in the code, I don't think. It's not. So let me just quickly go through this. If you're familiar with calculus, again, you would already know this, but you don't need to know calculus to understand deep learning. You just need to understand slopes. And I think everybody understands slopes. If you're on a hill, things fall down the hill. The derivative is simply a measurement of how sharp the hill is. And usually it's not in 2 dimensions or 3 dimensions, but in millions of dimensions, but it's still the same idea. The gradient is the direction of which you should go to increase or decrease the loss, right? Uh, Gradient points to the steepest increase, but so you like have to take the negative of that to get to the loss, but that's just a detail. So it's nothing but this mathematically, it's a derivative of the loss function derivative by each of the weights in your model. Again, these are probably billions in big models. Could be smaller, but it's going to be lots. So you're not going to do this by hand. You're going to let the computer do this. And that's one of the beauty of things like JAX. That NumPy doesn't have this, but this is something that JAX, PyTorch, um, TensorFlow, all these things bring to the table as a way to calculate these derivatives for you. If you express your model in there with their primitives, it can calculate these derivatives. Here's just a visualization of this. Like, you step here, you're just kind of wandering down to find the low point in the loss function. The one thing is it's called stochastic gradient descent. The gradient descent part, I think we understand, just go downhill in the loss function, but we can't fit all the data into our memory at one time, so we use small batches of them. And so we don't really get the right direction. We get a direction for that batch, may not be the correct direction. So we'll actually be jump like this when we're showing. The path will be stochastic, it'll be jumpy, noisy. And as far as the particular way you do that, well, you could just straightforwardly say, hey, just give me the gradient and I'll multiply that by some number and that'll be how much I adjust on my weights. That's one way to do it. There's better ways to try to take advantage of how fast I was going in the previous steps to try to get some momentum going. And then you can adapt the learning rate parameter and you can combine those together. Adapting meaning like in some places I should go faster because the slope's kind of low. In other places when the slope's really steep, I better slow down so I don't like overshoot and go past the minimum. So this atom is very commonly used. It combines both the momentum and this adaptive learning method. The, the details of how these work, I don't know if that's a topic for the book or not. Well, I guess we'll see. But it's at this point they're almost a commodity. You can just try them and take them off the shelf. Every deep learning library has these available for you. They're not that terribly difficult to understand, but in some sense you gotta don't you have to focus your efforts? You can't learn everything, can't know everything. Try as you might. There's one issue, of course, is that these loss functions for these deep neural networks are not convex. So there's multiple minimums and you're gonna end up probably in some kind of local minimum. There's really nothing much you can do about it. It's not really a problem. Uh, Often local minimum that you find is good enough. If it's not, you could try some kind of simulated annealing or something and try to push it into another minimum, but I never found anyone doing that too much in practice with these models. So I don't think it really happens that much. This is just a detail to me, I think. I don't know why he brings this up because, yeah, people used to worry about it and try to learn how exactly the derivatives are taken, but you don't have to worry about this because the system does this for you. It just calculates the derivatives. So, yes, it uses the chain rule and to go to compute back the graph, but the early neural networks, which are simply only combinations of these uh, ReLU uh, I should say, what should I say? Dense networks, right? You did this by hand, but it was actually pretty easy because all the gradients were pretty simple. You could actually backpropagate this using this chain rule. It's called the backpropagation algorithm. And I guess the point of that is that you propagate forward to calculate the loss, then use the gradient. Those gradients propagate backward through the network from the output to the input, adjusting the gradients. So it's not just a detail because it is important to be aware of the fact that for deep networks, there's something where the effectiveness of that back propagation dwindles as you get further and further and deeper networks. So it's important for that point of view. But the frameworks will do this for you. That's the key part. But this backward flow is kind of important to keep in mind to help you understand, diagnose certain problems that might occur. The so-called vanishing gradient problem, where the gradients they start out big at the beginning, but then as it back propagates to the network, they get smaller and smaller and smaller and have less effectiveness on the training. And there's things you can do about that, which I'm sure we'll learn about. One of them is this thing called a ResNet, a residual connection, to try to bring those gradients back further. Okay, so chain rule. I think we talked about that enough. Okay, so let's go back to understanding what's happening here with that original line in the code where we said to fit the model, take the training images, take the labels, do it for 5 epochs, and batch size 128. Now you know what's going on. There's 128 images drawn from the training data for each loop. That's what the batch size does. Then we go forward. We take the input, we run it through the matrix multi. These are matrix multiplication, okay, plus bias, matrix multiplication plus bias. Sorry, I left out the important thing. Then we do the element-wise ReLU, matrix multiplication. Then we do softmax. I haven't talked about that, but that's another sort of element-wise thing. We're just converting the output numbers, which are real numbers from minus infinity to infinity, to probabilities. You actually probably seen this. It comes up often in machine learning. And then we get our predictions. And we take our predictions, we compare them to the labels with this cross entropy loss. Again, not expected to know that yet, what that means exactly, but it's just a loss function that compares the predicted probabilities to the actual predictions. And then compute the gradients for all, in this case, there's 40,000 parameters. This is a very small model, by the way. So we're already at 400,000 parameters. Then the RMS prop is adjust all the weights, and then we just keep repeating that until we've done all, in this case, 469 times through to get through all 60,000 images. That's the process. All right, so now I'll go back. Leave these discussion questions for later. We still have some time. Now let's just do this. I see. Okay, great. So again, we'll just start over again. Took the images. Now you know what this thing is. This is nothing but a matrix multiplication of what's 20 by 20? I always forget. 500 and something, right? Wait. Seven hundred eighty-four. So this layer is a 784 by 512 matrix. That's what it is. Plus a bias term, plus adding a constant for. That's so what it's going to do is going to take this 784, which is that flattened image, multiply by that matrix, and then apply this element-wise maximum, right? Take all the negative elements and to turn to zero. That's all that does. Then it's going to take that output vector, which is now 512. That's the representation, very thin layer, but we have this is the hidden layer. 512. We took a 784 number, 784 length vector, and now we turn it into 512 length vector through this linear operation, and then we squashed all the negatives. Now we're going to do another matrix multiplication. This one's 512 times 10 matrix, and that's going to take the 512 numbers and put it into 10 numbers. 10 numbers, that's how many choices we have. We have 10 different possible digits. That's why we want to do that. But those numbers are going from minus infinity to infinity, so we use this softmax function to just simply map those to 0 to 1 and normalize it. That's all that does. I don't know if the book describes in detail what that is, but it's actually a really simple mathematical operation. And that's it. That's the model. Did I define this? No. Now we're going to compile it. We're going to use Atom Optimizer. Remember, that's the one that uses momentum and uses, I forget now, momentum and adaptive, right? Adaptive and momentum, ADAM, same thing. It's not some guy named Adam. And we're going to use this cross entry lock we didn't talk about, and we're going to use accuracy as the metric, which means percentage that you got right. And train it for, what the heck? I want to say the wrong button. Train it for 5 epochs, 5 times through the whole data with batch sizes 120. We've already done this. I don't know why I ran this again, but anyway, that's that. Now we can actually step back a little bit, and this is kind of fun to do, to try to do it ourselves a little bit in NumPy. Or not NumPy, I'm sorry, using Keras variables, which in this case will be using TensorFlow variables. So what we're going to do here is represent what everything I just said in words. Let's just do it, right? So I'm going to define my own dense network. And we're going to, this is an object. I don't know how familiar with Python, but we're just going to, don't worry about that part. Don't worry about the details. The point is we're going to, inside this dense network, it's going to be a weight matrix, W. Stop highlighting like that. W. And it's going to have shape of input size times output size. In this case, we're going to set the input size to be, when we use it, actually, this is very generic, we use for anything. Any input size and output size. And it also has a bias, which is just size output size. In other words, it's A times X plus B. This is the B part, or W times X plus B. We're going to initialize this one to be uniformly random, and this one just to be zeros. And when we use it, we will be using the matrix multiply. This comes from Keras ops. Matrix multiply. This is like I just said, right? Take the inputs, multiply it by this matrix W, add B. And if there's an activation function, apply it element-wise. Very straightforward, I think. Right? Does that make sense to you, Betsy?
Yes, it does. It does.
The idea, I think, of this chapter is to try to take some of the mystery away. Not all of it, but at least some of it. Strip off some of it. That's what I got out of it. Strip off
Yes,
some of
it,
it.
it tries to demystify some of the concepts, which I think
Yeah,
they did a really good job at.
yeah. And so here we are going to define our own version of the sequential operator, which we used before. Remember way up here, sequential, boop, let's do our own. So I would do our own sequential thing. And that's really nothing but, hey, for each layer, I'm just going to save it. And I don't do anything until you call me. That is apply it to an input. In which case, I'm just going to call each layer individually and it's in sequence. X, take X, apply the first layer, get X back, the new X, save it. And then do that. Oh, sorry, do that over and over again for how many layers you have. That's it. That's all it's doing. Piping through the layers. And this is just a way of, this property thing is a way of getting the weights out, which we'll need for doing the gradient descent. So here we go. We just define our own model and we're done. Now, the next thing we have to do is batch generating. So we're going to find our own batch generator. This is a lot of lines, but really all it's doing is simply taking the images and reshaping them actually, it doesn't even do that at all. Just saves the images and saves the number of batches that you're going to need. So the number of batches, the batch size you tell it, the number of batches it just does this floored or ceiling division on it. And then when you ask for a batch, that's when I'm going to slice it. I'm surprised it doesn't shuffle it, but maybe it's not important. I don't think it actually is important. Sometimes they do shuffle them and sometimes they don't. So all we're doing is slicing the images and labels and returning those pieces of it. That's it. Nothing big deal. I mean, it's worth studying the code in a little detail, but it's maybe not. So let's see. During learning, we're going to define a learning rate, this small learning rate. And this is, we're just going to use the most simplest possible learning rate. We're going to take the weights and then subtract the gradient times the learning rate, where the gradient is going to be given to this function. That's it. And for optimizing this, we're going to use SGD, give it the learning rate. So we're not going to define our own optimizer, but SGD does essentially this. Actually, we're not going to use this, I don't think. No, okay. I know, I remember now. This point was just to show you how it looks, what SGD does, but rather than do this, which is might be slow, we're just going to use the built-in optimizer from Keras. We still do the same thing. Because see, we redefined update weights here to use this rather than using our own one. Okay. Now, the only tricky part really is the gradient, right? So we're not going to try to take the derivative of that thing. Instead, we're going to use TensorFlow's built-in gradient capabilities, which is pretty much the main, well, the two main things of TensorFlow or PyTorch or JAX or any of these other, are there a lot of other ones? Maybe there's not. Those three give us is one is GPU, the other one is gradients. If you ask me, those are the two main things. So uh, to do gradients in TensorFlow is a little bit different than how you do it in PyTorch. It's a little bit different how you do it in JAX. So that is something I think will be talked about in the next chapter. But in TensorFlow, this is how you do it. You start a gradient tape and you tell it you want to watch a particular variable. Then you do your operations, whatever they are, with those. Now remember, these variables are not normal variables anymore. They're TensorFlow variables. So it knows when it's in one of these contexts to start watching for operations, and it'll keep track of all the gradients that happen. And then you can report it later. So I don't think this actually works when I did it for some reason. Oh, it did work. Okay. So, and lo and behold, yes, the gradient of y with respect to x is 2. That's basic calculus. And that's what it gives us too. We don't need calculus. We got TensorFlow. So with that whirlwind introduction, and I don't know that it's worth spending a lot of time understanding this because Keras is going to hide a lot of this for you unless you, and in fact, maybe you never use TensorFlow. So why learn this? Learn Jack's version of it, right? So, and I would probably recommend that. But for this case, we're using TensorFlow. So we're going to make our one training. This is our one training step. So we've got in a training step, what we're going to do is we're going to take our images batch, the labels batch, and our model, apply the model to the images batch, use the labels to calculate the loss, and then take the gradient and update the weights with that with that gradient. So let's walk through that real quickly. So we start a gradient tape because we want to keep track of derivatives. And then we call the model, which remember was a function because it had to call, it overrode the call dunder call thing. So when we call model on images, it's going to go through and do all those matrix multiplies and everything. That's where it happens. And out pops the predictions, which are this vector of probabilities, right? But when it's doing that, TensorFlow is keeping track of all those operations and calculating, so it can calculate the derivative at the end. Then we calculate the loss. Again, this is inside this gradient thing. So this loss is another function that's defined in TensorFlow. All the operations that are involved in this loss, whatever they are, they're not complicated, but whatever they are, it doesn't matter. TensorFlow will keep track of and allow us to calculate the gradient later. And this one too, we're taking the mean, we want the average loss. This operation is something that TensorFlow will keep track of the derivatives as well. And then finally, we say, okay, did all that, give me the gradients with respect to the model weights. And we update it using those model weights, using the update function we had. And then here we're just returning the loss. So we want to keep track of that when we're training. Did I define this? I must have defined some of them. Okay, so we can use our training loop that we just made, one training step to make a loop. And that's what we're going to do. There's our own fit thing. It takes the same arguments, model, images, labels, how many epochs, and batch size. And then we just use the batch generator to get our batches. And then for each batch, we're going to call this, here it is, one training step and reduce the loss each time. We'll print the loss every 100 batches just so you can see how we're doing. And then we can run this. And hopefully it all works. Yes. So this is all running in this notebook. The only thing we took a shortcut on, if you want to call it that, is we did not try to work out the derivatives by hand. Okay. That's the only real thing that we took a shortcut on this. Otherwise, we're doing it from scratch. And you can certainly, in fact, maybe if I remember, I'll try to find that. There's a really great YouTube video where it really walks you through, including the gradients, if you really want to do it from scratch. But you see the losses are going down. Eventually, they're up at epoch 5, epoch 6. How many epochs are we doing? 10. Okay. Might take a minute. But we're at the end of the notebook, so we're good. When it gets done, we'll see what the accuracy was. We'll see. It's not as good as it was when we used the TensorFlow thing because we had to be a little bit more. Uh, we're not using Atom. We're using the simpler SGD. We are using smaller batches and these things together just to make it so it can run on a notebook, but uh, in the Scratch way. But it still works. That's the key thing. Is it done? Yeah, 84% still. And this is nothing but saying, hey, running on the test images, the prediction is whatever one has the biggest value, and then all you have to do is just compare them, right, to get the accuracy. And some of them are wrong. 16% of them are wrong. Shame, shame. Okay, so that's that in a nutshell. Let's see, there's some discussion questions that the Claude made up that I've not looked at. I don't know if these are valuable or not. Why do we use mini batches instead of the full data set? I think the reason is they don't fit in the memory, right? I believe that's why. It'd be too
Yeah.
slow. Um, what happens if the learning rate is too high or too low? What do you think about that one?
I would imagine if it's too high now we jump a lot. So and then if it's too low, we might just if you're stuck in like a local minima, it's gonna be hard to get out. I'm just imagining that drawing now. Like if you're jumping too much now, you might just jump. If you are learning too slow, then you might just take a while. I'm not sure if
I agree. I think that's basically, yeah, too high, you might just jump right past the minimums. Too low, it could just take forever for one thing. And like you said, too, you might just, slowly wander down the wrong area too. I think that's good. That's good. Good answer to that. And here's another one. Uh, why are GPUs so effective for neural network training? Why are they? I actually don't know. I mean, I assume that's because there's special purpose hardware for doing matrix multiplication, uh, which is
yeah, I've
involved.
also just assumed this. I don't think I've thought about it this way. Why is GP so effective?
Well, GPUs were designed originally for graphics. That's from the name, right? Graphics, and graphics
Yes,
involves
yes.
a lot of rotations and translations and of vectors. So they're optimized for doing matrix multiplications. And yeah, it makes sense that I guess that's why their hardware special purpose for doing matrix multiplication would help for neural network training, is what I would say.
Yeah,
But
that makes
don't quote me
sense.
on that. Any other thing about the book you want, anything about the chapter? I really monopolized the heck out of that so-called discussion. I really wanted to make it a discussion, but like you said, it's a long chapter, so I kind of wanted to go through it, but I should have maybe put more room for discussion in there, so I apologize. But is there anything you want to discuss? Now's the time.
I think because it was just the two of us, then it was fine. Because I was also not able to go through the full chapter. So maybe if there was like a lot of people, probably then it was gonna be
Yeah, that's
more of a
true.
discussion.
Yeah. So, I mean, it was a good
Yeah.
chapter, right? I mean, the point was just to try to remove some of the mystery, I believe that, and also, well, what were the objectives? Learn what tensors are, and learn the basics of the training loop, and yeah,
Yes,
that's
yes.
what we did. So, I think in future chapters we'll go more deep into it, so to speak, the deep learning book.
Yeah. No, I enjoyed it. I think I just need to go finish the rest of the chapter and examples. But yeah,
Okay.
it was a good chapter.
And so I hope people will sign up for like next week's still open. And then actually, I think the fourth week is the one that only someone has signed up for, which I'm glad for. But